5,160 miles. Drawn as a line across a globe, that distance curves. It does not run straight. It follows the slow bend of the Earth's surface from the cold edge of the Antarctic Peninsula, northward and westward across open ocean, up through the tropics, until it ends at the warm coastal waters off Colombia, where the sea is the color of deep jade, and the air above it is soft and humid, and thick with the smell of a continent nearby. If that line were pressed flat against a map of North America, it would stretch from the southernmost tip of Florida to a point somewhere past the Arctic Circle, past the tree line, past the last road, and a single humpback whale swam it. One animal without pause. Without a map drawn by any human hand. The track was retrieved later from a satellite tag, a small device no larger than a thick book that had been attached to the whale's dorsal fin before it left the feeding grounds, and the data came back as coordinates, as numbers, as a thin curved line arcing across a hemisphere of blue. That line is among the furthest single displacements ever recorded for any warm-blooded animal on the surface of this planet. The whale covered roughly 50 to 60 miles each day, moving at a cruising pace that does not look like effort from a distance. The flukes rise, they fall. The body moves forward with each downstroke, the whole mass of it, 30 tons or more, advancing through the water in long, slow surges, as unhurried as breathing. At that pace, the journey from Antarctic ice to equatorial warmth took something close to 3 months. 3 months of open ocean. 3 months with no solid ground beneath or beside, only the changing quality of the water itself, the temperature of it, the color, the depth, the faint mineral signatures carried in the currents, the whole ocean like a text written in gradients and pressures, available to any body attentive enough to read it. The sea it left behind is among the most productive stretches of water on Earth. Down near the Antarctic Peninsula, in the long polar summer, the light reaches the surface for 18 or 20 hours each day and drives an explosion of microscopic life that feeds krill in vast deep water aggregations, dense enough in places to turn the ocean red-brown from the surface. A whale feeding in that water is filling itself in a way that has almost no equivalent anywhere else on the planet. The sea there is cold, close to freezing in some months, and the air above it is gray and raw and scoured by wind. But the food is there. The food is extraordinary, and for a few months each summer, the great whales are there to take it. Then the light shifts, the days begin to shorten. Something changes in the quality of the world that no human observer standing on a research vessel would consciously notice, but that arrives in the whale's body as a signal, clear, insistent, older than the current shape of any continent. And the whale leaves. It enters open ocean and begins to move north. The distance it will cover, 5,000 miles in one direction, is not a distance that maps easily onto anything in ordinary human experience. To cross the continental United States from coast to coast takes roughly 3,000 miles. The whale's one-way journey exceeds that by more than a third. The round trip, south again in the coming year, when winter is over and the ice has retreated and the krill have returned, will cover more than 10,000 miles in total. Some humpback populations complete round trips closer to 8,000 miles. The numbers vary depending on where a given individual feeds and where it breeds, because the ocean is not uniform and the whales are not identical in their routes. But the scale holds. These are animals that cross hemispheres as a matter of biological routine. Consider the gray whale, which travels a different ocean along a different coast and follows a different arc entirely. The gray whale moves along the western edge of North America, keeping the continental shelf within reach for most of its route. Its feeding grounds lie in the Bering and Chukchi Seas, shallow Arctic waters above Alaska, where nutrient-rich sediment supports dense populations of tiny amphipods that the whale scoops from the seafloor with its coarse baleen. When autumn comes to those latitudes, the light fails fast. The water cools. The ice comes early or late, depending on the year, but it comes, and the gray whales move south, pressing down the coast along a corridor that has been used by their kind for so long that the root is worn into their lineage as surely as their bones are. The lagoons at the other end of that corridor lie in Baja California, shallow, warm, sheltered from swell, ringed by desert, where the whales will give birth and nurse their calves in water that is 20 degrees warmer than anything they have left behind. From the Bering Sea to Baja California, one way, the gray whale travels between 5,000 and just under 7,000 miles. The round trip runs to 14,000 miles in some years. 14,000 miles in some years. Pressed against a map of the equator, that distance would carry a traveler more than halfway around the planet. It is the longest regularly documented migration of any mammal by one measure, and it is completed by animals that breathe air, that nurse their young on milk, that carry warm blood through their bodies against the cold of the deep sea, just as the land mammals they share their ancestry with have always done. The blue whale moves differently still. Its migrations are less rigidly mapped than the gray whale's coastal procession or the humpback's equatorial crossing, and the distances show more variation between individuals and ocean basins. Some blue whale populations tracked in the southern hemisphere travel 3,000 to 5,000 miles between Antarctic feeding grounds and lower latitude wintering zones. The corridors they follow are deeper and wider than the gray whale's nearshore corridor. They move through open ocean, through water that is blue-black and thousands of feet deep beneath them, far from any continental shelf. They are the largest animals that have ever lived on Earth, and in open ocean they become nearly invisible. A research vessel can pass within half a mile of a blue whale and see nothing from the deck but the blowhole's faint mist catching the light before it disperses. Their migration passes through a world that has almost no human witnesses, and the satellite tracks that document it are still, in many regions, sparse. What those tracks make possible, among many other things, is arithmetic. Not the arithmetic of maps, but of energy. When a researcher knows how far a whale must travel before it reaches feeding grounds again, and roughly how long it will spend at the breeding latitude without taking in substantial food, the minimum caloric reserves required before departure can be calculated. A humpback female that will travel 10,000 miles round trip, nurse a calf through its first weeks of life, and fast throughout. She must arrive at the feeding grounds in late spring, already carrying the fuel for all of that. The blubber she will accumulate over the course of a polar summer is not excess, it is inventory. It is the stored arithmetic of every mile she has not yet swum. That arithmetic matters for another reason. When the full spatial range of a migrating whale is known, the feeding grounds, the transit corridor, the breeding grounds, the return route, it becomes possible to map where the animal's life intersects with other things. Ship traffic, fishing gear, the acoustic disturbance of sonar and seismic surveying. The spatial scale at which these threats become relevant to a whale is not a bay, or a harbor, or a national park boundary. It is an ocean, conservation threat, an animal path meet somewhere on a hemisphere-spanning arc, and the migration track is the tool that makes the intersection visible. Without the track, the whale in transit is invisible. With it, The invisible becomes a thin, curved line on a map, carrying a name or a number, a departure date, a series of positions, and the line is long enough to cross through the boundaries of 4 or 5 nations, to pass through waters governed by different laws and different enforcement capacities and different levels of attention. A single individual whale lives inside all of those jurisdictions without knowing any of them exist. It moves according to something far older than any boundary drawn on any map. There is a word for what whales do, and it is not wandering. It is migration, and the distinction matters more than it might first seem. Nomadism moves in response to local conditions. The herd goes where the grass is, follows the rain, drifts along the edge of what is available, without a fixed destination. Migration moves according to a different logic. Migration has a destination, it has a departure time, it has a return, and the remarkable thing, the thing that satellite telemetry has documented across species and populations and individual animals tracked year after year, is how steady that timing is. The same humpback whale, tracked across consecutive years, departs the Antarctic feeding grounds within a narrow window, not on the same calendar date to the hour, but within days. The local temperature may vary. The krill density may be high or low. The sea ice may be farther north or farther south than average. Short-term variability in every measurable local condition can swing across a considerable range from one autumn to the next. And the whale leaves anyway. It does not wait for the ice. It does not wait for the food to thin. Something in the length of the day has already spoken, and the body has already answered, and the departure is underway before any external cue has reached a threshold that would register as a reason. This is what makes migration different from any form of responsive movement. It is not a reaction. It is a schedule. The animal carries the schedule inside it, encoded over millions of years of selection that favored the ones who left at the right time and arrived at the right place for the right conditions, not because they were smart enough to reason about it, but because the ones who did not leave, or left too late, or arrived too early, did not pass their timing on. The schedule is old. It is embedded deeper than behavior. It runs in the background like the rhythm of a heartbeat, and it does not ask for permission from the weather. A satellite track retrieved from a tagged humpback shows this in a way that is hard to fully absorb. The same stretch of Southern Ocean mapped across 3 consecutive years. Each year's track is slightly different, a different curve, a different set of daily positions, a different angle of departure from the feeding area. The ocean is not the same ocean from one year to the next. The currents shift, the temperature fronts move, the ice retreats by a different margin, and yet the tracks converge. They arrive at the same equatorial waters, in the same ocean basin, within a few days of each other across all 3 years. The variation in route is real. The fidelity of destination is also real. Both are visible in the same data. The humpback whale does not use the same path each time. It uses the same endpoint, the same season, the same vast equatorial warmth at the end of the same months of transit. Route and destination are separate things in the whale's migration, and the destination is the thing that holds. Now consider the ocean itself from the perspective of a blue whale traveling through it in mid-transit. No continental shelf below. The seafloor is thousands of feet down, further beneath the whale's cruising depth than any mountain on land stands above sea level. The water column above and below extends far beyond any light that penetrates. The whale moves through this space at a depth that is neither the surface nor the bottom, somewhere in the dimly lit intermediate layer where temperature and pressure create gradients that carry information about where the cold, productive water lies and where the warm equatorial shallows wait at the end of the crossing. There is no horizon in ocean depth. There is no landmark. There is only the slow shift of physical properties in the water around the animal's body, and the certainty, quiet, internal, unhurried, of a direction. The Antarctic Peninsula, from which the 5,000-mile humpback track departs, is a place at the edge of the world's coldest ocean. The ice in winter extends out from it in all directions. The sky in summer is almost continuously lit. The water is iron-rich from glacial meltwater and supports blooms of phytoplankton so dense they color the sea. It is a place of extraordinary biological energy, available only seasonally, and the whales that exploit it must leave before that energy vanishes. The tropics toward which they move are warmer and calmer, and by the measure of primary productivity, far less rich. The open equatorial ocean is sometimes called a desert, blue, clear, beautiful, and relatively empty of the dense food concentrations the whales need to fuel their bodies. They travel toward a food desert from a biological banquet, and they do it because the desert is also, for reasons that have nothing to do with food, the right place to be. There is something in that geography, the vast unproductive warmth at one end, the cold, dense richness at the other, that captures the essential paradox of great whale migration. The distances are not incidental. The distances are the whole point. The separation between feeding and calving habitat is precisely what the migration has evolved to span. Close them and the selection pressure that produced the journey disappears. The journey exists because the best place to eat and the best place to be born are not the same place. They are an ocean apart. Distances of this order have been measured precisely only in recent decades. Before satellite telemetry, the migrations of great whales were inferred from whaling records, catch locations correlated by season, animals marked at one site and harvested at another, statistical patterns in sighting logs that spanned years. Those records were useful. They were also incomplete, and they were acquired at a cost that reduced many populations to fractions of their former size. The tags that now document the distances are small and temporary. They attach and release, or they transmit until the battery fails, and what they return is a record, a departure, a transit, an arrival, a series of positions plotted across the hemisphere that show, with the precision of mathematics, the scale of what these animals do. The precision carries weight. An approximate migration distance, somewhere between 8 and 10,000 miles, is a different kind of knowledge than a specific track of 5,160 miles from a specific peninsula to a specific coast on a specific date. The specific track anchors the wonder in something real. It removes the suspicion that the numbers are estimates, that the truth might be less extreme than the claim. The satellite says, this whale, this distance, these coordinates, this day. The line on the map is the whale made visible. The ocean does not look like it holds this kind of precision. Standing at the edge of it, at any shore, facing any open sea, what is visible is sameness. The water extends to the horizon in all directions and suggests nothing about what moves through it. The surface gives very little away. A whale moving at depth 50 miles offshore might as well be on another planet, from the perspective of any person standing on the beach. The evidence of its passage is invisible from the shore. There is no wake that persists. There is no track in the water. By the time any satellite position is transmitted to a receiver orbiting the Earth and transmitted back to a researcher's screen, the whale has moved on, and the water where it was has closed back over itself, and the surface is again unbroken. This is one of the things that makes the satellite track something other than mere data. It is the record of a presence. It says there was something here, traveling, alive, covering this distance in this time, at this depth in this ocean. The track on the screen is not the whale, but it is evidence that the whale was real, and the journey was real, and that both of them were larger than anything that had been visible from the surface. The gray whale's route has a particular quality not shared by the more open water humpback track. It runs along a coast. For most of its length, the western shore of North America is within a few hundred miles, sometimes within sight of land, or close enough that the shallow sea floor of the continental shelf is a constant presence below. The route has been traveled by gray whales for long enough that the archaeological record of indigenous peoples along the Pacific coast includes these animals, drawn into relationships of hunting and ceremony and ecological attention that go back thousands of years. The migration corridor is not just a whale's path, it is a path that runs through human time as well, through the long coastal cultures that built their worlds at the edge of the sea and learned over generations when the gray whales would come. That nearshore quality gives the gray whale's migration a texture different from the open ocean crossings of humpbacks and blues. The coastal corridor is pressed against the continent like a ribbon of travel, a thin zone of purposeful movement laid along the western edge of a landmass. From inside the corridor, the ocean is bounded on one side. The whale is not surrounded by open water in all directions. It has a wall, soft, underwater, the gradual rise of the seafloor as it approaches the shore, and that wall is part of the navigational structure of the journey. At the southern end of the corridor, in the lagoons of Baja California, the quality of the water changes so completely that it is almost impossible to reconcile with what lies at the northern end. The lagoons are shallow and warm. In winter, they are sheltered enough that the swell is minimal, the surface calm, the water clear. The desert of the Baja Peninsula surrounds them on land, low and dry and brown. The gray whales that arrive there have been swimming for weeks, and they arrive at warmth, at calm, at shallow water, at the conditions that a newborn calf will need before it has had time to build any reserves of its own. Blue whales, crossing mid-ocean far from any shelf, encounter neither the coastal texture of the gray whale's route nor the dramatic hemispheric arc of the humpback's Atlantic or Pacific crossing. They move through a different scale of experience, one measured not in proximity to coastlines, but in the width of ocean basins. Their migration, in some populations, is a movement between the nutrient richness of the Southern Ocean and the comparatively quieter lower latitudes, where wintering occurs, and the space between those two zones is simply ocean in the fullest sense of the word. Deep, wide, lit from above for a few hours each day in the higher latitudes, and many more as the whale moves north, carrying its vast body through water that shifts from frigid to cool, to merely cold before the tropics begin to warm it. The blue whale at depth in mid-ocean is in a place that has almost no equivalent in human experience for its quality of isolation. The seafloor below is further down than many mountains are tall. The surface above is visible only as a faint brightening in the water. In all other directions, there is only water, water at varying temperatures, varying pressures, carrying varying concentrations of dissolved salts and gases and the faint acoustic signatures of distant sources. The whale moves through this with a body that is longer than 2 school buses and weighs more than the largest land animals that have ever existed. It moves with a kind of ease that belies the distances it covers, its flukes rising and falling, In that same slow, steady rhythm, the whole body progressing through the ocean with no apparent destination visible in any direction. The distance of its migration is measured in ocean basins, not in coastline segments, not in the number of nations whose waters are crossed, though that number is real. In the raw physical span of an ocean, measured from cold pole to warm equatorial zone, in the kind of units that only make sense at the scale of a hemisphere. All of this, the specific 5,000-mile humpback track, the 14,000-mile gray whale round trip, the open ocean crossing of the blue whale through the deep mid-Pacific or mid-Atlantic, shares a single essential quality. It is regular. It repeats. It is not a response to an exceptional event, not a flight from unusual conditions, not an opportunistic movement following an unpredictable food source. It is a schedule kept year after year, departure and return, high latitude to low, and back again, driven by something inside the animal that is older than any map of any ocean ever drawn. That is the thing that distinguishes migration from every other form of long-distance movement. The nomad follows what is available. The migrant follows a calendar. The calendar is not a human invention in this context. It is encoded in the length of the day, in the animal's hormonal response to light, in the finely tuned departure timing that evolution has refined over millions of years of selection. The whale does not decide to leave. It does not weigh the food remaining against the distance ahead. It simply leaves, on schedule, because the schedule runs inside it, because the body knows before the ocean shows any sign of what is coming. A tagged humpback, departing the feeding grounds on a clear autumn day off the Antarctic Peninsula, enters the open ocean with no fanfare visible from above. There is a blowhole's exhalation, a brief column of vapor dispersing in the wind. There is the fluke's final rise as the animal descends, and then the surface is smooth, and the whale is gone from any visible world, carrying its 30 tons and its months of stored fat and its internally encoded certainty southward or northward into the open sea. The satellite above records the first position, and then the next, and then the next. The track begins to extend across the map. Day by day it curves, following a path that no researcher assigned and no chart prescribed, set by the animal's own navigational reckoning in the absence of any landmark that a human eye could identify. The track will run for weeks. The track will run for months. It will end, eventually, in warm tropical water far from the ice, in a place where humpback whales have been ending this same journey for longer than the current species names for them have existed. Below the ship lanes and the weather systems and the surface light that a satellite can measure, in water that is cold and dark and vast and quiet, the whale moves steadily north. It does not hurry. It does not slow. The ocean has no roads, and it needs none. The departure is made, the direction is held, and the distance ahead is simply the distance ahead, not a challenge, not a feat, but the ordinary shape of a year in the life of an animal whose body was built over millions of generations precisely for this crossing. Some years the track curves a little differently. Some years the whale arrives at the equatorial breeding grounds 2 or 3 days earlier than the year before, or a few days later. The route shifts, the curve of the track shifts. What does not shift is the arrival. What does not shift is the season of departure. What does not shift is the fundamental geometry of the year. Cold, productive south, warm, quiet north, the crossing between them, and the return. This is fidelity made visible in lines of data. The slight variation in each year's track shows that the whale is responding to the real ocean. its actual temperature fronts and current variations, its particular conditions in a particular year. The consistency of the destination shows that something deeper than response is operating, something that will bring the same animal in the same months to the same warm equatorial waters, regardless of what the ocean between there and the ice has done. The track says this animal was here and here and here, and arrived here and will, when the cold season comes again to the tropics and the wheel of the year turns south, begin the whole arc again. One afternoon, in whatever month the year dictates, in whichever ocean holds this particular animal's route, the feeding in the Antarctic stops being productive enough to justify staying. Or perhaps it stops before that. Perhaps it stops when nothing in the external world has changed at all, when the krill are still dense, and the water is still cold, and there is by any visible measure no reason to leave. The light is simply shorter than it was, by a margin too fine for any instrument of ordinary attention to detect. The change is real. The body knows it. The season is turning, and the whale turns with it. It enters the open water. It begins to move. The ocean ahead is hundreds of millions of square miles of surface and billions of cubic miles of depth, and somewhere inside that vastness is a place the animal has been before, or that its lineage has been for so long that the knowledge of it has become something closer to instinct than memory. The departure is not dramatic. There is no visible ceremony of leave-taking. There is only the whale, in the ocean, moving, steadily, rhythmically, as if the distance were nothing at all. The distance is 5,000 miles, and the whale swims it. In the last weeks of polar summer, in the shallows of a cold and krill-thick sea, a humpback whale feeds with a patience that has no urgency in it. The water here is green and cold and loud with the movement of small things. Light comes through it in broad-angled shafts that do not reach the floor, and the whale moves through this light like something the ocean made for itself, slow, enormous, utterly at home, its body doing the quiet, necessary work that will carry it across a hemisphere before the sea freezes again. The blubber is building. Day by day, through weeks of feeding that begin before sunrise and continue past the fading of the last cold light, a layer of lipid dense tissue thickens along the whale's flanks and belly and back, accumulating beneath the skin in a band that is already several inches deep and growing still. It is not fat in the casual sense. It is a biological reservoir, as precise in its chemistry as anything the body makes, dense with stored energy, arranged in layers of varying composition, each one optimized for different rates of release over the long months ahead. A large humpback in peak summer condition may carry a blubber layer 4 to 6 inches thick along its main body. The layer is not uniform. It is thicker at the sites where it insulates the most critical tissues. It is organized as all the body's deep preparations are organized by time and purpose and the slow pressure of selection across millions of years. To feed at this rate requires extraordinary water. The sea at high latitude in summer is one of the most productive ecosystems on the planet, cold water welling up from depth, carrying dissolved nutrients that fuel the growth of phytoplankton at the surface. The phytoplankton feeding krill in dense concentrations that the whale filters from the water in long explosive lunges. A single lunge may process thousands of gallons of seawater through the baleen plates, straining out the krill and letting the water go. The whale does this again and again through the hours of the day. It does this for weeks. It does this until the body has stored what the body will need, and the body, which knows things the mind of any observer cannot access, knows when that threshold has been crossed. The storing is the preparation. The preparation is already the journey, in some sense, because without these weeks of feeding, the journey cannot exist. There is no migration without the blubber that funds it, no crossing of 8,000 miles of open ocean on an empty reserve. The whale does not eat again, or barely, and incidentally, for the entire duration of transit and breeding and the long return, some females, those who will conceive and nurse and then travel back toward polar water with a calf at their side, lose between a quarter and a third of their total body mass across the full arc of that cycle. The blubber is not merely fuel for swimming, it is the food source for milk. A nursing humpback mother transfers energy from her own stored blubber into the calf through milk that is nearly 50% fat. Milk so rich it supports a growth rate in the calf that has almost no parallel among mammals. All of that comes from the summer's accumulation. All of it is stored, invisibly, in those thickening flanks before the whale has taken a single southward stroke. And so the body builds what the journey will consume in a sea that is cold and generous and briefly full of the food that makes everything else possible. Something else is happening in the body at the same time, something invisible and internal and entirely independent of how much krill is in the water. As the weeks of summer lengthen and then, almost imperceptibly, begin to contract, the light changes. The Arctic and Antarctic days that stretched nearly to midnight begin giving back their hours in small increments. The daily window of sunlight, which at midsummer reached its greatest breadth, narrows by minutes each day as the planet continues its slow orbit. Most of those minutes pass without any visible event. The water does not change color. The krill are still there. The temperature of the sea is still near its summer high. Nothing about the immediate environment signals that anything has ended or is ending. But in the whale's brain, the changing light has already been received. The ratio of daylight to darkness, what biologists call the photoperiod, acts as the master clock for the annual biological cycle in many animals that live at latitudes where seasons are pronounced. In the whale, as in many other long-distance migrants, this environmental signal enters through the eye and is processed deep in the brain, where a small region of nervous tissue tracks the daily pattern and compares it against the pattern of the days before. The shortening of the light window, not the cold, not the ice, not the absence of food, but the changing ratio of light and dark is what tells the body that the year has turned. It is the most reliable signal available in a world where weather varies, where prey densities fluctuate, where temperatures shift from year to year in ways that carry no consistent information. The photoperiod is the one thing that does not vary. It runs on astronomical time, governed by the angle of the Earth relative to the Sun, and it has been running without interruption for as long as the planet has had seasons and animals have lived beneath them. What the changing light sets in motion is a cascade of hormonal signals that begins in the brain and moves outward through the body over days and weeks. The hypothalamus, reading the photoperiod through a series of neural relays, adjusts its output of signaling molecules. The pituitary gland responds, altering the release of hormones that govern the gonads and the thyroid and the adrenal tissue. Melatonin levels, which rise during dark hours and fall during daylight, shift in their daily pattern as the nights lengthen. Luteinizing hormone and follicle-stimulating hormone, both involved in reproductive physiology, begin their seasonal adjustments. The thyroid changes the pace of metabolism. Cortisol shifts in ways that alter how the body allocates energy between immediate activity and long-term storage. None of this is visible from outside. None of it makes any sound the ocean can carry. But the body is reorganizing itself in preparation for something it has not yet begun, a preparation that runs ahead of any environmental cue that a cold weather watcher might think of as the trigger. This is what biologists mean when they speak of migration being an internally organized event. The whale does not wait for the ice. It does not wait for the water to turn cold enough to make feeding uncomfortable, or for the krill to thin to the point where the cost of staying outweighs the cost of going. By the time any of those things happen, the body is already committed. The hormonal program has already altered the whale's physiology in ways that cannot easily be reversed. The drive to move south, which is not a decision in the way a human being decides to leave a place, but rather a state of the body that increasingly makes remaining in place untenable, has already been encoded in tissue and chemistry. The departure, when it comes, arrives as the completion of a process that began weeks before, invisibly, in the narrowing of the daily light. Satellite telemetry has revealed how closely this internal timing is kept, year after year. Tagged whales depart their polar feeding grounds within narrow windows, often within a few weeks of the same date in successive years, even when local conditions vary substantially. A year of unusually high krill abundance, a summer that runs slightly warmer or slightly colder than average, an early or late onset of sea ice formation. None of these factors shifts the departure date by more than the small range that the internal program allows. The body keeps its own calendar, and it keeps it by the light. Water temperature does play a role, but it is a secondary one, a fine-tuning signal laid over the internal program rather than the master cue itself. Gray whales have been observed departing their northern feeding grounds slightly earlier in years when ocean temperatures drop more quickly, and lingering modestly when prey concentrations remain unusually dense. Across baleen whale species more broadly, thermal gradients in the ocean, the boundaries where cool water masses meet warmer ones, appear to influence the choice of specific routes during transit. But these are adjustments within a range already defined by the hormonal program. The whale moves south because the body has told it to move south, and the temperature of the water it encounters along the way shapes the details of how it travels, not the fact of its departure. There is something settling in this, the idea of a biology so well matched to a predictable celestial rhythm that it needs no other signal to keep time. The planet tilts, the light shifts, and somewhere in polar water, a creature measuring 40 feet and 50,000 pounds begins, invisibly and irreversibly, to prepare for one of the longest journeys made by any warm-blooded animal alive. Far from where the whale is feeding, in warm water at the edge of the tropics, a different kind of biological event is either ending or about to end. The breeding aggregations at humpback wintering grounds in waters like those around Hawaii, or the Caribbean, or the island coasts of West Africa or Brazil are dispersing or are about to disperse. The males have been displaying for weeks long and energetically costly bouts of surface activity and vocalization that compete for the attention of receptive females. Females who were bred in the previous season have been nursing calves that are now several months old and visibly growing. Females who conceived in this season carry early pregnancies that will develop slowly over the coming year. And the youngest calves, the ones born just weeks ago into calm, warm, shallow water, are thin-flanked and still learning the mechanics of breathing at the surface, still dependent on their mother's milk, still far too slight and poorly insulated to survive the cold. Humpback whale calving in these tropical breeding grounds is timed across the population between December and April. The timing is not arbitrary. It is a product of the same hormonal and photoperiodic program that governs departure from the feeding grounds, a program that synchronizes conception, gestation, birth, and lactation, so that by the time mother and calf must begin the return migration toward polar water, the calf has had enough weeks in warm, shallow, calm seas to accumulate the beginnings of its own blubber layer. The milk has been doing the work. The fat in the mother's blubber has been moving via the milk into the calf's developing tissues, building the insulation the calf will need when the water temperature drops from the low 80s of the Caribbean to the near freezing cold of the Antarctic summer sea. The timing must be close. Leave too early, and the calf has too little blubber to survive the cold. Leave too late, and the mother, already depleted from months of fasting and lactation, risks arriving at the polar feeding grounds too late in the season to recover sufficient reserves before the feeding window closes. The system has very little slack in it. The coupling between breeding phenology, when calves are born, and how long they nurse in the tropics, and latitudinal travel distance is one of the tightest biological calibrations in the natural world. A population of animals that breeds thousands of miles from where it feeds, that fasts for months during transit and breeding, that gives birth to the largest neonates of any mammal, this system works only because the timing is nearly exactly right. The calf in the warm water now does not know any of this. It surfaces to breathe in the slow, slightly clumsy way of the very young, rolling its rostrum above the waterline and drawing in air before sinking back. Its mother stays close. The mother is not resting. She is not eating, has not eaten for weeks, and is continuously monitoring the space around her calf with the low, slow attention of an animal that is both exhausted and acutely alert. The water here is warm enough that a human swimmer would feel comfortable in it, a temperature that sits more than 20 degrees above what the mother left behind when she departed the Antarctic in the autumn. It is this warmth that makes the calf possible. A newborn humpback has almost no blubber at birth. Its thermoregulatory reserves are minimal. In Antarctic water, it would not survive a day. In this warm, calm, sheltered sea, it has weeks to grow before the cold is asked of it. The warmth is not incidental. It is the reason the breeding grounds are where they are, and the reason the mothers travel so far to reach them. The geographic separation between feeding habitat and calving habitat, cold, productive polar sea on one side, warm, calm, predator-reduced tropical water on the other, is the engine that drives the entire migratory system. The distance is not a cost that evolution has failed to eliminate. It is the price of putting both things, abundant food and safe birth, in the same animal's life cycle, when those two things cannot occupy the same place on the planet at the same time. That logic, built into the body over millions of years of natural selection, is what the blubber is for. It is what the hormones are for. It is what the tight coordination of departure timing, transit speed, and breeding phenology is for. The blubber is the bridge between the two places the whale needs to inhabit in order to reproduce and survive. It is built in the cold, carried through the vast middle distance of the ocean, and spent in the warm first as fuel for transit and breeding, then as the raw material of milk, then as the calories that enter a thin-flanked calf, and slowly become the insulation that will one day carry that calf back north. The mother lies in shallow water in the early afternoon light, her calf beside her, the surface barely moving. Somewhere in her body, the processes that will initiate her return north are already beginning. The slowly shifting photoperiod of the tropical winter beginning to register in her brain's deep timekeeping structures. The hormonal program already laid on its next step. She does not move yet. The calf is not ready. But the signal has arrived, and the body is listening. And in the weeks that remain before departure, the calf will grow, and the reserves will diminish, and the internal calendar will continue marking the days with the only instrument it has, the slow, steady shortening of the light. There is a quality of ordinary miracle to all of this that becomes apparent when the full arc of it is held together. A creature that weighs as much as a loaded freight truck undertakes a fast that lasts half a year. It travels thousands of miles through open ocean on stored lipid alone. It gives birth to an animal whose survival depends entirely on the accuracy of an internal clock calibrated to the tilt of the planet. And all of this happens year after year, maintained by biology so well tuned to astronomical time that a change in the length of an afternoon is enough to set the whole cascade in motion. Consider what the blubber is in this light. In late summer, it is a bank being filled. Each day of feeding is a deposit, krill converted to lipid, lipid laid into tissue, tissue thickening under the skin, while the water around the whale is still cold and bright and full. The rate of deposition is not constant. In years when krill concentrations are dense and the feeding is efficient, the reserves accumulate faster. In years when prey is harder to find, when the productive upwelling zones are shifted by changing currents, or when the krill bloom is poorly timed, the whale enters migration with a thinner account. Body condition at departure has measurable consequences for what follows. Females who arrive at the breeding grounds in poor condition are less likely to conceive, and those who do are less likely to wean healthy calves. The blubber, measured at the start of a migration, carries within it a record of how the polar summer went, a biological archive of productivity and prey availability, written in the thickness of a tissue. By the time departure comes, triggered by the internal program, confirmed by the shortening light, adjusted only slightly by local temperature and prey conditions, the blubber has reached its peak. In a large, well-fed humpback, it may constitute more than a third of total body mass. It is the dominant tissue by weight that the animal carries into the water as it turns south. Everything that follows, the thousands of miles of open ocean, the weeks in the breeding aggregation, the nursing of a calf, will draw from this stored reserve, a fraction at a time, until the animal returns to the polar feeding grounds months later, and the cycle of accumulation begins again. It is useful to follow the lipid itself, to watch where it goes. Stored in the blubber under the skin, it remains relatively stable during the early weeks of migration. The whale's metabolic rate during steady cruising transit is elevated but not extreme. The animal is large, and large bodies lose heat more slowly than small ones, and the muscles required to sustain a slow, steady pace through water are efficient in their use of energy. But as the weeks of transit pass and the whale enters the breeding aggregation, the demands increase. Males engaged in competitive behavior burn energy at elevated rates. Females in late pregnancy are provisioning the developing calf from their own reserves. And when birth occurs and lactation begins, the rate of reserve depletion accelerates sharply. The blubber is being metabolized, converted back from stored lipid into the components of milk at a pace the body can sustain for weeks but not indefinitely. A nursing humpback mother is doing something physiologically extreme. She is producing, from her own stored tissue, a milk that is extraordinarily rich in fat, far richer than the milk of terrestrial mammals, because the calf needs to build insulation fast, and the window for doing so is limited by the approaching return migration. She is fasting while doing this. She is in water that is warm enough that her own thermoregulatory costs are low, which helps, but the caloric demand of milk production is high regardless. The loss of body mass across the full cycle, Departure, transit, breeding, nursing, return transit, arrival can reach a quarter to a third of the whale's total mass. In a large female, that represents tens of thousands of pounds of tissue metabolized and transferred first into transit and reproduction, and then into the growing body of a calf. The calf, for its part, is absorbing all of it with remarkable efficiency. In its first weeks of life, a humpback calf may gain more than 100 pounds per day. The rate of growth during this period has few parallels among air-breathing animals. The calf is converting its mother's stored lipid into its own tissue, muscle, organs, and most critically, blubber, at a pace that visibly changes the shape of its body over the weeks of the nursing period. When the pair finally departs for the return migration, the calf that swam at the surface with a thin, slightly angular silhouette has become a more rounded animal, its flanks beginning to carry the insulation that will allow it to survive the cold water ahead. The warm sea has done its work, the mother has done hers, and somewhere above and around them, the light has continued its slow astronomical business, the days gradually lengthening again as the southern hemisphere tilts back toward the sun, the photoperiod shifting its balance once more, the signal arriving in the mother's brain that the time is coming to leave. The ocean does not change in any way that a human observer on the surface could easily detect. The water is still warm. The sun still rises high and bright each morning. There is no visible sign that anything has changed or is changing, but inside the body of the mother whale, in tissues and cells, and the slow chemical conversation between brain and endocrine gland and organ, the preparation for departure is already underway. The same internal machinery that set her moving south in the autumn is resetting itself for the return. The hormonal program, which ran the breeding season with such precise timing, is entering its next phase. And the calf beside her, which knows nothing of Antarctic water or krill or the long cold summer ahead, will follow her north because following is all it knows to do, and because everything it needs for the journey has been placed in it, quietly and in advance, through weeks of extraordinary milk. This is one of the quieter truths of animal migration, that by the time any outward movement begins, the preparation is already complete. The body does not wait for the visible signal. It reads the astronomical one, the slow and reliable language of light, and it begins its preparations in the dark interior of its own cells, while the world outside is still giving no indication that anything is about to change. The whale feeds while the blubber builds. The whale nurses while the calf grows, and the light shifts by small fractions each day, fractions too small to see, too small to feel, too small to measure without instruments, and the body reads them anyway, because this is what the body has done for long enough that the response is now written into the deepest structures of the animal's biology. There is nothing urgent about any of it. The time scale is not a human one. The accumulation of blubber happens over weeks. The hormonal cascade runs over days. The growth of a calf from thin to round happens in a passage of warm tropical mornings that seems from outside entirely unhurried. And all of it is happening simultaneously in the bodies of thousands of animals distributed across the warm seas of 3 separate ocean basins, humpbacks in the Caribbean and the waters of the South Pacific and the Indian Ocean, all running the same program on the same astronomical signal, all preparing for departures that will carry them back toward water that is right now cold and green and full of krill and lit by a polar summer sun that will not last much longer. The calf surfaces and breathes and sinks back. The mother surfaces and breathes more deeply. The water is warm around them, and the air above is warm, and the light falls through the clear shallows in long, slow columns that shift and waver with the small movements of the surface. Everything here is as it needs to be, for as long as it needs to be. The system is not generous by intention, it has no intentions, but the fit between what the animal needs and what the place provides is so close that it looks from outside like care. The warm water holds the calf, the rich milk holds the cold at bay, the internal clock holds the timing, and when the time comes, the mother will move, and the calf will follow, and the vast ocean that lies between this warm sea and that cold one will receive them both and carry them forward, as it has carried thousands of their kind before, along routes that run through the body as surely as they run through water. The calf does not yet know the cold. It knows only this, the warmth, the milk, the steady presence of its mother's vast body, close beside it in the slow afternoon light of a tropical sea, and the mother rests as much as a fasting animal can rest, in the particular stillness of an animal whose body has done what it needed to do, and is now simply waiting for the program to reach its next step, the way a long and necessary process completes itself, not in a rush, but in a quiet settling into what comes after. The light will shift again tomorrow. The days are already, by small fractions, growing longer. And somewhere in the whale's brain, in the neural tissue that reads the light and translates it into chemistry, the signal is accumulating, patient, precise, as reliable as the orbit of the planet it reads, toward the threshold at which it will set everything in motion once more. The warm sea will be behind them, the cold, productive, ancient sea will be ahead, and between the two, carried within the body of the mother and the growing body of the calf, will be everything the journey needs, laid down in fat, written in time, held in the deep arithmetic of a biology that has been keeping this calendar longer than any human record has been kept. In every direction the water is the same. It runs to the horizon to the north, and the horizon to the south, and the horizon to the east and west, and every one of those horizons is identical, a thin gray line where ocean meets sky, offering nothing a traveler might steer by. No peak, no shore, no tree. The water is deep enough here that the bottom is 1.5 miles below the surface, invisible and irrelevant, a place the light gave up on 1,000 feet above. An animal moving through the middle of this place, breathing air, warm-blooded, heading toward a destination more than 2,000 miles ahead. That animal is navigating, not drifting, not wandering, moving along a line, a course, held steady across a blank and featureless ocean by something inside it that the ocean itself cannot provide. The question of how a whale finds its way is a question about information, not about maps in the human sense, drawn, stored, consulted, about the physical world itself as a structure dense with signal, and about a body evolved over millions of years to read that structure, to extract direction from phenomena that have no direction written on them in any visible form. The ocean looks empty. It is not empty. It is full of information, layered and overlapping, available to the right senses, and what lives inside a whale, distributed through its tissues and its brain, is precisely the right set of senses to read it. Deep in the tissues of several whale and dolphin species, researchers have found magnetite. These are crystals, naturally magnetic, biologically produced, each one a grain of lodestone, no wider than a few thousandths of a millimeter. They occur in clusters, embedded in tissue, and they are not an accident. Magnetite forms only under specific biological conditions, inside cells that have been found in the heads and along the lateral regions of the animals that carry them. The planet has a magnetic field. It extends from the core outward, through the crust and into the water, invisible and continuous, a three-dimensional structure that changes in measurable and predictable ways, with latitude, with distance from geological anomalies, with depth. A crystal of magnetite embedded in living tissue responds to that field. It aligns with it the way a compass needle aligns, not because it chooses to, but because its physical nature makes the response unavoidable. The animal carries, distributed through its body, a set of tiny compasses, and because the field shifts systematically with position on the globe, the information contained in that alignment is not only directional, but potentially positional, a way of reading not just where north is, but roughly where in the world a body finds itself. The evidence for this is not only anatomical. Along the coastlines of several continents, researchers have mapped the locations of cetacean strandings, the places where whales and dolphins have beached in groups or alone, and compared them with geological surveys of the seafloor and coast. The correlations are consistent. Strandings cluster more often along lines where the local magnetic field is distorted, where a geological feature near the coast has bent or interrupted the smooth, predictable gradient that a whale's magnetite might otherwise read clearly. A whale following a magnetic contour would, in such a place, be reading a signal that points the wrong way. It would follow that false signal toward shallowing water. The correlation does not prove the mechanism, and researchers hold it carefully as a hypothesis rather than a settled answer. But the anatomy is real, and the correlations are real, and the picture they point toward is one of an animal whose body is continuous with the planet's invisible geometry, reading the field not from outside, but from within. The ocean floor below a migrating whale is not flat. Nothing about the seafloor is flat. It is a landscape, ancient, vast, sculpted by forces that have been working on it for hundreds of millions of years, and it has the full complexity of a landscape, with its ridges and valleys, its sudden vertical walls, its gradual ascending slopes, its isolated peaks rising from deep plains. The mid-ocean ridges run for thousands of miles, mountain ranges that dwarf anything on the continents, most of their peaks below the surface. Seamounts rise from the abyssal plain, extinct volcanoes, solitary, sometimes tall enough to reach within a few hundred feet of the surface before falling back into darkness. Submarine canyons cut into continental shelves at angles, deep slots in the rock where cold, deep water moves in slow, upwelling currents. This topography is permanent. It changes on geological timescales, thousands to millions of years. For a whale whose ancestors have been migrating for millions of years, the shape of the seafloor is among the most stable features of the world, a fixed reference that does not shift with seasons or weather or the movement of prey. Gray whales, moving along the western coast of North America, appear to follow the contours of that coast, with a consistency suggesting they are reading the underwater margin of the continent itself, the shelf edge, the slope, the shape of the bottom beneath them. The gray whale is a shallow water animal, staying closer to the coast than the great open ocean species, and the bottom is never far below it. The acoustic properties of water allow low-frequency sound to travel enormous distances, reflecting and refracting through layers of different temperature and density. A whale producing low-frequency sound, and then receiving the echo of that sound returning from the seafloor, from the face of an underwater ridge, from the curved flank of a seamount. That whale has information, not a picture, not a sonar screen, but a pattern of returning sound that is different at every location, different over a sandy shelf than over rock, different beside a canyon wall than over open deep water. The pattern is a signature. A whale that has traveled this route before, or whose mother traveled it before, would have encountered that signature at the same place in the same sequence. It is possible to know where you are by what comes back. Researchers working in ocean acoustics have proposed that fixed geographical sources of consistent low-frequency sound could function as landmarks for animals with the sensitivity to detect them. Submarine volcanoes produce sound. The constant grinding fracture of geological activity along spreading centers produces sound. Where ocean swell breaks against specific coastlines and refracts around headlands, it generates a pattern of low-frequency microseismic energy that persists year after year, coming from a fixed point with a consistent acoustic signature. A whale navigating by these sources would be doing something analogous to a person navigating through a familiar city by the sound of a particular church bell or a particular intersection, not by reading a map, but by knowing that this sound means this place. Low-frequency sound, in the right conditions, travels thousands of miles through the deep ocean, carried through the Sofar Channel, a horizontal band of water at mid-depth, where the speed of sound reaches its minimum and where sound becomes trapped, bouncing between density layers, losing energy so slowly that it can cross an ocean basin without fading to nothing. A whale producing sound in the Sofar Channel and listening for the returns could be, in principle, reading a continent from 1,000 miles away. The hypothesis is not fully confirmed by direct evidence from free-ranging animals, but the physics is real. The anatomy suggests sensitivity in the right frequency ranges, and the consistency of migration routes over generations is the kind of result that demands an explanation. The eyes of a baleen whale are not human eyes. They are set on either side of a large skull, offering wide lateral vision rather than forward binocular vision. The retina is organized differently. Inside the eye, behind the retina, there is a reflective layer, the tapetum, that bounces light back through the photoreceptors a second time, increasing sensitivity in dim conditions, the same structure that makes cats' eyes glow in a beam of light. The photoreceptors include cells sensitive to wavelengths at the blue and possibly ultraviolet end of the spectrum. And in the physical structure of the lens and the arrangement of those photoreceptors, there are features consistent with the detection of polarized light. Sunlight passing through the atmosphere becomes partially polarized, its waves aligned preferentially in a plane that depends on the position of the sun. At dawn, the pattern of polarized light in the sky and at the sea surface arranges itself in a way that carries information about the sun's azimuth, even when the sun itself is below the horizon or hidden behind cloud. Many insects navigate by this pattern. Several bird species use it. A whale whose eye contains the right photoreceptor arrangement would, in principle, have access to a sun compass even in overcast conditions, even in the early morning or late evening when the sun's disk is not visible. Whether baleen whales do in fact use polarized light for navigation has not been confirmed by direct experiment in free-ranging animals. The experiments needed to test it in a 60-ton open ocean animal would be extraordinarily difficult to design, but the anatomy does not exclude it. It invites it as a possibility, and the multi-layered picture of cetacean navigation that is emerging, magnetic field, seafloor topography, acoustic landmarks, possible celestial compass, is the picture of a system that does not depend on any single cue, but uses all of them simultaneously, each one a check against the others. This kind of multi-cue navigation is not unusual in the animal world. Animals navigating across long distances tend to use redundant systems, magnetic, celestial, olfactory, visual, because each system alone is fallible. Clouds cover the sun. Magnetic anomalies distort the field. Familiar smells are absent in unfamiliar water. The animal that has only one system is more vulnerable to its failure than the animal that has four. What makes cetacean navigation worth contemplating slowly is the scale at which it operates. Not a few miles across a meadow, not a few hundred miles along a coastline, across an ocean basin, from one polar sea to another, with a stop at the equator, navigating by forces that are measured in thousandths of a degree of arc, by sound that has traveled thousands of miles and carried information that a moving body can read. The precision this implies is not small. It is the kind of precision that only becomes visible in what the animal does in arriving within days of the same date at the same location, year after year, across a lifetime. A humpback calf is born in tropical water, in the warmth of a breeding ground, in the season when most of the humpbacks that have gathered there from their feeding grounds are gathered still. It knows nothing yet in the sense of having learned anything. It knows how to breathe. It knows how to find its mother's flank and nurse. The ocean around it is warm and clear and shallow by the standards of the open sea, and the mother holds close, the two of them moving together with a slowness and proximity that marks them as a unit. But the calf is swimming. It is moving through water, and because it is beside its mother, it is moving through the water in precisely the direction its mother chooses, at precisely the speed its mother sets, along the path its mother's body selects from all possible paths. This is the beginning of learning. Not learning by instruction, not learning from symbol or signal, but learning by travel itself, by inhabiting the route. The outbound migration south from the feeding grounds is made by pregnant and newly nursing females, and these animals are among the most experienced in the population. They have made the trip before. They know the route not as an abstraction, but as a sequence of physical experience, a thermal gradient crossed here, an acoustic signature encountered there, a particular bottom topography appearing at a particular stage of the journey. When the calf swims south for the first time beside its mother, it is moving through all of those things too. The water temperature shifting along the route, the character of the sound environment changing as the depth below changes, as the seafloor rises and falls, the magnetic contour varying day by day. The calf developing nervous system is registering all of it, not consciously, not as a deliberate act of study, but as experience accumulating. Then the return migration back toward the feeding grounds, and the calf beside its mother again, covering the same route in reverse, the same signatures in reverse order. Researchers studying humpback populations have found evidence that the specific corridors populations use, not just the general north-south direction, but the particular arcs across the ocean, the preferred waypoints, the timing of passage through specific regions, are characteristics of populations rather than of individuals. Different populations use different routes, even when the routes would seem geometrically to cross. This kind of population-level route fidelity, passed from experienced females to calves over generations, is what researchers describe as cultural transmission of navigation. The word cultural is chosen carefully. It does not mean what culture means in a human context, with its full weight of language and artifact and deliberate teaching. It means that information about the route passes from one individual to another through direct experience, through accompaniment, and that this information is therefore something that can be lost. A population that loses its older, experienced females to hunting, to ship strikes, to entanglement in fishing gear, loses not just individuals but knowledge, the routes those females carried, the sequence of cues they had assembled across years of migration, the timing they had refined trip by trip. That information does not persist in a gene or a stone, it persisted in them. When they are gone, the populations that survive have to rebuild it, and the rebuilding takes time. And during that time, the corridors that generations of whales refined toward efficiency and safety may become diffuse, the animals spreading wider across the ocean as the cultural map that once guided them loses its detail. This possibility was examined in populations severely reduced by industrial whaling in the 20th century. Some of those populations have recovered in numbers. Whether they have recovered the detailed cultural geography of roots accumulated over centuries before the reduction is a harder question, and one that satellite telemetry is only beginning to allow researchers to approach. The tracks of whales in recovering populations show more individual variation in route selection than the tracks of populations that were never reduced to the same degree. The variation itself is not conclusive. Individual variation is normal, and the populations are at different stages of recovery. But the signal is consistent with what the hypothesis would predict. The ocean below the surface is not silent. It has never been silent. Water is a denser medium for sound than air, and the physical processes that produce sound, geological, biological, atmospheric, do not pause because there are animals nearby. Wind generates surface noise. Rain generates a white hiss across a wide frequency range. Geological activity at spreading centers and volcanic seamounts generates low-frequency rumbles. Ice grinding against ice in both polar regions generates grinding and cracking sounds that travel far beyond the ice. And layered on top of all of this is the sound made by the animals themselves, by the snapping of crustaceans, by the clicks of dolphins, by the low, slow calls of the great whales. In the Sofar Channel, at the right depth, this sound accumulates. It does not dissipate as quickly as it would at the surface. A low-frequency call produced by a blue whale in the Central Pacific can be detected by instruments and potentially by other blue whales thousands of miles away. Whether whales actively use this vast reach of sound for navigation, or whether the acoustic landscape they move through is primarily a byproduct of the physics, and they extract navigational information from it as an additional layer of available data, is not fully resolved. The two possibilities are not mutually exclusive. It is plausible that a whale both produces low-frequency sound that returns useful echoes from nearby seafloor features and simultaneously listens for the persistent, geographically fixed sources that the physics makes consistently available at specific locations across the ocean. The Sofar Channel, at its best propagation conditions in the deep central basins of the major oceans, is not a human-made structure. It is a property of water, the way temperature and pressure interact with depth to create a layer of minimum sound speed, bending sound waves downward from above and upward from below, trapping them in a corridor that runs at mid-depth across entire ocean basins. It existed before there were animals in the ocean. The animals that evolved in it evolved into a world that was already organized acoustically at the largest scales. A seamount rising from the floor of the Pacific is a physical object that reflects sound. A whale swimming above into one side of it would receive a pattern of acoustic returns that is different from what it would receive over open flat bottom, a brief brightening of the reflected signal, a change in its timing and direction, a shadow of acoustic information that marks the seamount as a feature in the water. If the whale has passed this seamount before, or if its mother has, and the calf absorbed the root's acoustic character during its first migration, the signature is familiar. Familiar means knowable, and knowing where a seamount is in relation to where you are going is in its most basic function, navigation. The mechanics differ entirely from what a human navigator does with a chart. The underlying operation, using known features of the world to fix a position and maintain a course, is the same. The surface of the ocean, seen from just below it in clear water, is alive with light. During the day, the patterns that light makes at the surface change with the depth and angle of the sun in a way that is predictable, stable, and continuous. Near dawn, when the sun has not yet risen, but the sky to the east is brightening, the polarization pattern of the light at the surface is at its most structured, the alignment of the light waves most pronounced, the compass information most legible to an eye that can read it. A whale moving slowly in the upper water column at first light, oriented in a particular direction, would have access to that pattern. Its eye, with the tapetal structure that enhances sensitivity and the photoreceptor distribution consistent with polarization sensitivity, would receive a signal that varies with orientation, that is stronger in one direction than another, that has a peak that shifts with the sun's movement, that a body could use to hold a constant heading. The evidence for this use in free-ranging baleen whales remains indirect. The anatomy is consistent with the capability. The behavior, specifically the reliable maintenance of course across featureless open ocean under varying weather conditions, is consistent with using it. The full experimental confirmation has not been built yet, and the uncertainty is real. What is clear is that the eye of a baleen whale is not designed for the same visual tasks as a human eye, and that the differences are not impoverishments, but adaptations to a different set of problems, one of which may be reading direction from light. Water temperature is something a whale's skin registers directly, not as an abstract measurement, but as a physical sensation, the thermal character of the water passing over the body, the slight shock of a colder layer encountered during a dive, the gradual warming as the animal ascends from depth into sun-warmed surface water. Across the open ocean, temperature is not uniform. It varies with depth, with the season, with the movements of large water masses, with the proximity of upwelling zones, where deep cold water rises toward the surface. At the boundaries between different water masses, where a current of warm subtropical water meets a tongue of cool subpolar water, for example, there is a thermal front. The front is not a wall. It is a gradient, sometimes tens of miles wide, where the temperature changes steadily from one side to the other. Animals moving through this gradient feel it. A whale that regularly crosses from tropical to polar water and back carries, in its history of thermal experience, a familiarity with what certain water temperatures mean about where it is in the world. Thermal fronts also concentrate prey. The boundary between two water masses tends to aggregate the plankton and small fish that form the base of the baleen whale's food chain, because the physical dynamics of the boundary stir nutrients upward and concentrate passive swimmers at the interface. A whale following a thermal front is therefore following a line that provides both navigational reference and feeding opportunity simultaneously. Satellite telemetry of humpback and blue whales has shown that their tracks frequently run parallel to detected thermal fronts, sometimes for days, the animal moving along the boundary rather than crossing it. Whether the whale is following the front because of the prey it concentrates, or because of the directional information it provides, or both at once, these motivations are difficult to disentangle from external observation. The behavior itself is what the data shows. The track, the front, and the parallelism between them. By the time a whale arrives at its destination, the low-latitude breeding grounds, or the high-latitude feeding grounds, depending on the direction of travel, it has navigated successfully across a hemisphere using no single instrument but many, none of them infallible in isolation, all of them usable together. The magnetic field told it roughly where on the planet it was. The acoustic character of the seafloor told it which stretch of bottom it was passing over. The thermal structure of the water told it which water mass it was moving through and where the boundaries were. If the sun was visible, it may have provided a check on direction. If the water was clear and the light was right, the polarization pattern at the surface may have provided another. And somewhere behind all of this, encoded not in any external signal, but in the body and the brain, was the root itself, the learned sequence of things to expect, and when to expect them, accumulated over a lifetime of migrations, and before that, over a calf's first migrations beside its mother. A mother and her calf move through open water on a night passage. The stars are not visible. There is cloud and no moon. The surface of the ocean is dark. There is nothing for a human eye from the surface to distinguish from any other stretch of open sea. The mother's flukes rise and fall in the steady rhythm of a cruising whale, unhurried, covering 30 miles in a day. The calf matches that rhythm, riding close, the two of them moving as a single shape through the dark. The mother knows where she is. Not because anyone told her, not because anything is written on the water, but because she has been here before, and because the ocean, to a body as finely tuned as hers, is not a blank. It has a texture, a magnetic grain, an acoustic character, a thermal quality, a quality of light when the light comes. The route she is following is not only her route, it is the route her mother followed, and her mother's mother, refined generation after generation by the survivors, the whales who found the feeding grounds and the breeding grounds and came back, whose calves lived, whose calves' lived, each journey adding a small increment of precision to what was already precise. The route being traveled tonight is older than any human record of the ocean. It is older than the coastlines that the whale does not need to see. It predates the harbors and the shipping lanes and the faint mechanical hum that runs through the water at all hours now, added to the acoustic landscape in the last 100 years. The whale and her calf move through all of that and through the older ocean beneath it, through the fixed acoustic signatures of seamounts and ridges that have not moved in 10 million years, through the magnetic gradients that reflect the deep history of the planet's core, through the thermal boundaries that shift with seasons and decades, but return reliably to the same general geography year after year. The calf will make this crossing dozens of times in its life if it lives the full span of a humpback whale, which may be 80 years or more. Each migration will deepen the knowledge in its nervous system, the route growing more detailed, more certain, the recognitions faster and more sure. When it is old and experienced, it may travel with a precision that seems from a distance like something other than what it is. It will not look like an animal doing something effortful. It will look like an animal going home. And it will be. But home, in this case, is not a fixed point, but a path across a hemisphere, traveled and retraveled until the path and the traveler become indistinguishable. The ocean holding the memory of the passage as surely as the whale holds the memory of the ocean. The clouds shift and break. Somewhere near midnight, a pale wash of reflected light settles across the surface of the water. Not bright, not directional, just the diffuse illumination of a partially open sky. The mother's back breaks the surface in a long, slow arc, and the breath rises and disperses in the dark air, and the back submerges again without a sound. The calf surfaces a moment after her, smaller, its breath quicker and lighter. Then they are both below the surface again, moving south, together along a path that the calf does not yet know is a path, that it is learning without knowing it is learning. The way any young creature learns the shape of the world it will spend its life in, by being carried through it, slowly, close to something that knows the way. The ocean continues in every direction, unchanged on its surface by the passage of two animals through its depths. The water moves, the planet's field extends through it, steady and invisible, orienting the crystals in the tissue of two moving bodies. The sound of the deep seafloor returns faintly from below, different here than it was yesterday, different tomorrow than it is tonight. The route is not on the water. The route is not in the stars. The route is assembled, each night and each day, from 100 quiet signals that only that body in that ocean can read, a piece of knowledge that is also a piece of history, carried forward in the only way such things are ever carried, across the dark water, from one living body to the next, along the edge of a continental shelf where the seafloor drops away into water too deep for light to reach. A thin ribbon of cold rises. It comes from below, from depths where the water has been sitting in darkness for a very long time, pressed down by the weight of everything above it, slowly cooling against the rock of the ocean floor. When the wind blows parallel to the coast and the surface water is pushed away from the land, this deep cold water has nowhere to go but up. It rises slowly and steadily along the shelf edge, carrying with it everything it has dissolved over years of sitting in the dark: iron, phosphorus, nitrate, the mineral residue of matter that has fallen from the surface world and been broken down in the deep. Where this cold water meets the light, something happens that is visible from space. The surface turns a different color, greener, cloudier, darker at its heart, as billions of microscopic plants bloom in the sudden wealth of nutrients. The bloom spreads outward from the upwelling in slow spirals, and the creatures that feed on those plants gather below the surface in dense, drifting layers, and the ocean at this place is briefly one of the richest on Earth. A humpback whale, moving south through this water, senses the change before it is visible. The temperature drops a degree or two. The sound of the ocean shifts, more clicks and scatter from the organisms thickening in the water column below. The whale slows. Its southward momentum, which has been steady for days, eases as it turns slightly into the current. For a short time it feeds, opening its pleated throat against the concentrations of small fish and krill. Its body, already carrying the fuel of months of summer feeding, takes on a small additional reserve. Then it turns south again, resuming the long line of its migration, with its flanks slightly fuller than before, the upwelling falling behind it as a patch of dark water on a brightening sea. This kind of pause is common along migration routes, and it matters more than it might seem. The ocean along a migratory corridor is not uniform. It is a series of distinct water masses pressed against one another, each with its own temperature, its own chemistry, its own load of life. Some of these water masses are poor, warm, clear, low in nutrients, nearly empty. Others are briefly rich, lit from below by upwelling, or stirred by currents that bring cold, productive water to the surface. A whale traveling through them is not moving through a featureless medium. It is crossing a landscape as varied in its way as any continent, and the body reads the changes as clearly as any traveler reads a change in terrain. The condition a whale arrives in at its breeding ground is not simply a function of how much it ate in the summer. It is also shaped by what the corridor offered during transit. In years when the upwelling zones along the migration route are strong, when the deep water rises early and the blooms are dense and the prey layers thick, Whales that pause to feed arrive at lower latitudes in better condition. The caloric reserves they carry into the months of fasting that follow the breeding season are larger. Females in better condition are more likely to conceive, and if they conceived the previous season, they are more likely to carry calves that survive. The ocean the whale swims through is not background, it is part of the outcome. The gray whale's coastal corridor runs close to the shore, and along its length the upwelling zones are well mapped. Researchers who study the relationship between oceanographic conditions and whale body condition have found that even subtle variation in upwelling intensity in a given year leaves a signature in the animals themselves, in blubber thickness, in reproductive rates, in the survival of calves born the following winter. The ocean's generosity or restraint in one season ripples forward into the next. It is a slow arithmetic, written in fat and fertility, accumulated over the length of a journey that covers many thousands of miles. Where the upwelling fades and the water warms and the corridor opens into blue oceanic desert, the whale does not pause. It moves through these stretches at its cruising pace, roughly 100 miles a day for a gray whale, somewhat less for the larger humpbacks, steady and unhurried, spending blubber in small measured amounts, breathing in a rhythm as regular as tide. The empty ocean is not a threat. It is simply a stretch of the route where the currency of effort flows in one direction only, outward from the body, and the whale is built to sustain that flow for a very long time. A thermal front appears in satellite sea surface temperature data as a sinuous color boundary that can extend for hundreds of miles across open ocean. On one side of it, the water is several degrees warmer. On the other, it is colder, often more productive, fed by deeper water mixing up through the boundary layer. The front itself is not a wall, it is a gradient, a place where two water masses press against each other without fully mixing, and along which prey tends to concentrate. Small organisms follow the slight thermal advantage. Fish follow the small organisms, and whales, reading the temperature boundary through their skin and through the acoustic properties of the water around them, tend to travel along these fronts rather than across them. Satellite tags placed on humpback and blue whales have returned tracks that follow thermal fronts for days at a time, the animal moving parallel to the color boundary visible in the satellite imagery, holding to the colder productive side, turning when the front turns, neither crossing into the warm water nor abandoning the boundary for the open ocean on its other side. The front provides orientation, it concentrates food. It may also serve as a kind of loose pathway through water that otherwise offers few directional cues. Moving along it, a whale is not making a decision in any deliberate sense. It is responding to a thermal gradient, registered in the skin, and the response that was selected across long time, the one that persisted because the animals that made it arrived in better condition than the ones that didn't, is to follow the cold side of the boundary, southward. The front curves and then straightens again over several hundred miles. The whale follows it, its flukes rising and falling in the same unhurried cadence. The front grows indistinct as the water masses gradually equilibrate, and then it fades entirely, and the whale is in open ocean with no thermal guide, moving by other reference now, magnetic, acoustic, remembered, toward water still many hundreds of miles to the south. There are places along migration corridors where the ocean is not simply indifferent, it is busy with traffic that has nothing to do with any biological calendar. The Santa Barbara Channel, which lies between the California mainland and the northern Channel Islands, is one of the most heavily trafficked shipping lanes on the Pacific coast. Container vessels move through it at speeds of 15 to 25 miles an hour, their hulls running deep below the surface, their propellers turning in water that gray whales and blue whales and humpbacks have used as a migration corridor for far longer than any port has existed on that shore. The ships cross the channel in both directions, day and night, in all seasons, without reference to what moves beneath them. At 15 miles an hour, a vessel covers the width of the channel in under 2 hours. A whale at its cruising depth may hear the approaching ship, but low-frequency propeller noise overlaps with the frequencies a whale uses for its own orientation, and the sound comes from all directions in a channel bounded by land on 2 sides. The strike, when it happens, is rarely perceived by the crew. The hull registers a slight shudder. The whale registers nothing. It is found later, sometimes floating, sometimes stranded on a beach, sometimes not found at all. Population-level estimates of ship strike mortality are systematically lower than the true number because the majority of strikes produce no evidence recoverable by any observer. Researchers tracking whale movements through the Santa Barbara Channel have placed satellite tags on blue whales and compared the resulting tracks with vessel traffic data for the same period. The tracks intersect. Sometimes a whale's southward line crosses a shipping lane at an angle, and the tagged animal appears in the data on the far side of that crossing point, its signal continuing for weeks afterward. Sometimes the tag goes silent at the intersection, and the reason is not always recoverable. The data shows what the ocean looks like when 2 entirely different systems of movement are imposed on the same water at the same time, one operating on biological time and the other on commercial time, neither aware of the other, both following their own logic through the same channel. Efforts to reduce ship strikes in this corridor have included voluntary speed reduction programs in which vessels slow to 12 miles an hour or less through the densest portions of the whale migration zone. At lower speeds, the force of impact is reduced, and the time available for both whale and vessel to adjust course is slightly greater. The effectiveness of these programs depends on participation, and participation varies. The whales move through regardless, as they have moved through the channel for as long as the channel has existed, their timing governed by internal signals that have not changed and will not change in response to anything a vessel does. Off the central California coast, at a particular headland where a submarine canyon comes close to the shore and the water depth drops quickly from the shallows to the deep, a group of transient killer whales sometimes hold station in early spring. They have been documented at this location in multiple years, arriving when the gray whale migration passes through its northward phase, when the long line of returning whales, adults and calves, moves along the coast from Baja California toward the Bering Sea. The killer whales are not numerous. A group might be 4 or 5 individuals, sometimes fewer. They wait in the dark green water near the headland, and they wait for the same reason any predator waits at a crossing point, because the crossing point will come to them. The gray whale calf is vulnerable in a way the mother is not. It is several months old by the time the northward migration begins, born in the warm lagoons of Baja California, fed on milk that is among the richest produced by any mammal, already substantially larger than it was at birth. But it is still small by comparison with its mother, and it is still learning to navigate, and it tires more quickly than an adult, and when it surfaces to breathe, it surfaces more predictably, on a slower schedule, in a position that can be anticipated by an observer who knows the timing. The transient killer whales know the timing. They have learned it, or inherited the knowledge of it, or both. The attack, when it comes, is not brief. Transient killer whales isolate calves from their mothers through sustained, cooperative effort, one or two individuals working to keep the mother occupied, while others work on the calf, driving it toward the surface when it tries to dive, preventing it from breathing on its own schedule, wearing it down over the course of an hour or two or three. The mother stays. Gray whale mothers have been observed remaining within a body length of their calves throughout attacks that last more than an hour, positioning their own bodies between the calf and the attackers, surfacing to breathe, and diving again in a pattern that mirrors the calf's. The attachment does not waver. Humpback whales are documented to approach and engage with killer whale attacks on gray whale calves and on other species, sometimes arriving from a distance and driving themselves between the attackers and the prey, sometimes lifting a seal or other smaller animal out of the water on their backs. The behavioral pattern is consistent enough across observations that it has been studied formally, and researchers have noted that it occurs across populations and in encounters where the humpback has no clear relationship with the animal being attacked. The explanation for this behavior is not fully settled. What is clear is that humpback whales respond to the signals of a killer whale attack with a physical approach and an apparent willingness to insert their own large bodies into the encounter, and that this response is costly in terms of energy and carries some physical risk. The transient killer whales off the California headland are part of a relationship between predator and prey that is older than any record of it. Gray whales have been passing this headland on their northward migration for a very long time. The killer whales or their predecessors have been waiting here for an overlapping span of time, and the behavioral adaptations on both sides, the cow swimming close to shore in the shallows where the larger orcas cannot easily maneuver, the orca group positioning itself just beyond the shallows at the depth transition, have been shaped by that long shared history. Neither side shows any sign of the other ceasing to exist. The predation takes some calves and not others, and the gray whale population continues its annual transit, and the killer whales hold station at the headland in the right season, and the season comes again. Moving south from the California coast, the corridor splits. Some humpback whales follow the arc of the continental shelf edge, staying within a few hundred miles of the coast, where the bathynyptera provides reference and where opportunistic feeding is possible near the shelf edge. Others leave the shelf behind entirely and move into open pelagic ocean, taking a straighter line toward the tropics across water that is thousands of feet deep and largely empty of the features that make coastal travel legible. The two routes look very different in satellite telemetry data. One shows a track that curves gently with the coastline, spending days in the vicinity of shelf edge features, pausing occasionally. The other shows a nearly straight line running toward the equatorial breeding grounds, covering open water at a pace that does not slow. The choice between these routes is not random. Body condition plays a role. An animal in excellent caloric reserve may have less reason to follow the food-adjacent coastal route and can afford the efficiency of the straight pelagic line. Reproductive status matters. A pregnant female or a recently nursing mother may follow different decision rules than a young adult in its first or second migration. Individual experience contributes. Whales that have traveled a particular route before may follow it again through whatever memory or behavioral template guides that repetition. And the local ocean matters. A year in which the shelf edge zone is cold and unproductive may shift the balance for animals that would otherwise have used the coastal arc. At the scale of the whole population, both routes produce arrivals at the same breeding grounds. Humpbacks tag-tracked from the same Alaskan feeding area, departing within weeks of one another, have been recovered months later at the same Hawaiian or Mexican breeding waters. having traveled paths that diverged by hundreds of miles in the middle section of the route and then converged again at the destination. The ocean is large enough to contain both solutions to the same problem. The breeding ground is small enough that the two solutions find each other there, and the population assembles from its dispersed mid-ocean paths into a concentration of animals in warm, shallow water, gathered for a different biological purpose entirely. The pelagic route carries its own character. Away from the shelf, the water is very blue, a deep, clear, saturated blue that indicates low productivity, low particle load, high transparency. The sunlight penetrates to considerable depth in this water, but there is little for it to illuminate beyond the water itself. At depth, the pressure is steady and enormous, and the temperature is cold and nearly constant, and there is very little sound from biological sources. The whale moves through this water for days without the acoustic texture of a populated ocean. The low-frequency sound of distant swells moves through the Sofar Channel below and around it, and occasional ship noise arrives from far away, and the deep geological murmur of the seafloor carries through the rock and up into the water column. But the biological chorus that is present in productive coastal areas is largely absent here, and the whale's travel through this part of the route is a kind of passage through a very large, very quiet room. The open ocean at night, seen from the surface, gives very little back. No coastline, no shelf break, no visible reference. Stars, if the sky is clear, and the slow heave of swell, and the sound of the animal's own breathing in the dark. A whale traveling this passage does not require external reference the way a human traveler does. The navigational apparatus it carries in its tissue, the magnetic sensitivity, the acoustic map built from infrasound reflections off geological features far below, the thermal gradient registered in the skin provides sufficient orientation to sustain a straight course across water that offers the eye nothing. The animal does not experience the open ocean as featureless. It is reading a different version of the landscape than any surface observer would perceive, one written in magnetic field intensity and the low-frequency echoes of distant ridges. Days pass in this passage. The water around the whale warms gradually as the latitude decreases, not abruptly, not at any single moment, but in the slow accumulation of degree by degree across hundreds of miles of southward travel. The color of the water changes too, through increments invisible from inside it, the deep blue of the oligotrophic open ocean giving way, eventually, to the lighter, slightly more turbid color of tropical water, where river plumes or coastal upwelling touches the offshore zone. The animal's skin registers the warmth. The flukes, rising and falling, push against water that is 5 degrees warmer than it was a week ago, and then 10 degrees warmer, and then the water is warm enough that a human entering it would feel it immediately as a different element, generous and enveloping rather than cold and bracing. The breeding grounds that assemble in this warm water are not silent. They are dense with acoustic activity, though none of it the kind this script is asked to address at length. The relevant fact here is spatial. The animals converge. A population that has spent the polar summer dispersed across hundreds of thousands of square miles of productive feeding sea, and that has crossed thousands of miles of ocean individually or in small groups, arrives at a relatively compact tropical area within a matter of weeks, drawn there by the same internal signals that sent them from the feeding grounds in the first place. The convergence is one of the most reliable biological events in the North Pacific, or the North Atlantic, or the Southern Ocean, year after year, generation after generation, regardless of what the specific conditions of any given crossing were. Along the Hawaiian breeding grounds, Researchers have documented humpback whales arriving within a narrow window of dates that shows surprisingly little variation across years of very different oceanographic conditions en route. Animals that had productive crossings and animals that had lean ones arrive within weeks of each other. The timing is driven by the internal hormonal program, by the photoperiod signal processed in the brain during the feeding season, translated into a departure schedule, and then maintained through transit, by whatever internal calendar governs the pace. The ocean along the route can offer more or less, but it cannot significantly advance or delay the biological agenda of arrival. The same convergence happens in the southern hemisphere, where humpback populations feeding in Antarctic waters depart on a similar schedule, modified for the reverse seasons, and travel north along the western coasts of South America and Africa, and through the central Pacific toward tropical breeding areas around New Caledonia, Tonga, and the waters off Ecuador and Colombia. The satellite track of an individual humpback from the Antarctic Peninsula to the Colombian Pacific coast, a one-way distance of roughly 5,000 miles, describes a curve across the surface of the ocean that, rendered as a line on paper, looks simple. The line is a compression of weeks of sustained travel, of shifting water masses and thermal gradients and depths that vary from a few hundred feet over shelf edges to several miles in the open ocean trenches, of nights in the open Pacific with no light and no reference but the internal geometry of a navigating body. At the far end of that line, in the warm, shallow waters off the Colombian coast, the whale that traveled it enters the breeding aggregation. It is in different condition than it was when it left Antarctic waters, lighter, its blubber somewhat reduced, its systems reorganized around the hormonal demands of breeding rather than the metabolic demands of feeding. It is also in company, suddenly, after weeks of relatively solitary travel through open ocean. The water around it contains other humpbacks, and the acoustic environment shifts accordingly, and the biological purpose of the whole long arc of migration begins. On the other side of the same ocean, in the same season, a blue whale is crossing the South Pacific. It is larger than any other animal alive, perhaps the largest animal that has ever existed, and it is traveling with the same steady, unhurried purpose as the humpback, covering hundreds of miles a week through water that varies in temperature and productivity as the route descends from Antarctic latitudes toward lower latitude wintering areas. Blue whale migration routes show more individual variation than humpback routes do. Different individuals have been tracked to quite different destinations, and some populations appear to move shorter distances than others, remaining at higher latitudes year-round when prey conditions support it. The pattern is consistent in its broad logic: feeding areas at high latitude, wintering areas at lower latitude, while varying considerably in its specifics. The blue whale at depth in mid-ocean moves through water that is dark and cold and under pressure enough to compress the lungs of any air-breathing animal that dove to similar depths without the adaptations to manage it. The whale manages it. Its blood carries oxygen in concentrations that allow a dive of 20 to 40 minutes before the animal must return to the surface, and its physiology is organized around the alternation of surface and depth in a rhythm as natural as any other aspect of its biology. The surface, when it reaches it, is light. The depth, when it descends, is dark. The migration carries it through both, day after day, for weeks, along a route laid down in its biology by selection pressure that has been working on this lineage for a very long time. Ship traffic cuts across blue whale routes, as it cuts across humpback and gray whale routes. The risk is proportional to the overlap between where whales concentrate and where vessels concentrate, and in many ocean basins, these two distributions are far from random in their relationship to each other. Ports are built where coastlines and depth contours are favorable, and those same features, shelf edges, upwelling zones, temperature fronts, concentrate whales. The shipping lanes that lead to large ports therefore tend to pass through productive coastal waters that are also important to whale populations at some phase of their annual cycle. The coincidence is geographical, not deliberate, and it has been producing mortality that is difficult to quantify for as long as large vessels and whale populations have shared these waters. The routes are older than the ports. The ports are older than the traffic levels that now pass through them. The whales do not adjust. Their departure timing does not shift in response to the density of vessel traffic in their corridor, any more than it shifts in response to local food conditions. The signal that sends them is internal, and it has been reliable for long enough that the behavior it produces is deeply fixed. The ocean they cross now contains things it did not contain for most of the time the migration has existed, and the whales cross it anyway because the signal says to cross it, and the signal is not reading the shipping lanes. Two whales setting out from the same feeding ground on the same October day might not see each other again until they arrive in the same tropical waters months later. In the interval, one travels a coastal arc close to a continental shelf, feeding opportunistically when upwelling zones are active, pausing near shelf edge features where the bathymetry provides navigational reference. The other strikes out across open pelagic ocean, taking a straighter southward line through water that is deep and clear and largely empty, covering the distance more directly, spending blubber faster, but arriving without the delays that coastal feeding pauses introduce. Both solutions are viable. Both have been made before by whales of this population and whales of every generation before them, and both produce the same arrival at the same warm water, where the biological calendar resumes its next phase. The cross is the same ocean. It holds the same thermal fronts, the same upwelling zones, the same shipping lanes, the same patient predators at the same crossing points, the same stretch of open pelagic blue that gives back nothing to the eye but depth and light. It is also, in each crossing, specific, a particular configuration of water temperature and prey distribution and vessel traffic that will not repeat exactly in any future year. That is the product of this season's winds and currents and the accumulated conditions of years of ocean circulation. The whale crossing, it is not navigating an abstract route. It is navigating this ocean in this season with the route as a biological template that must be expressed in the specific conditions of this particular year. Where the corridor narrows in a channel like the Santa Barbara, pressed between islands and a mainland, the specificity of the moment is most apparent. The water is shallow enough that ship traffic and whale traffic are sharing not just the same ocean basin, but the same column of water, a few hundred feet of sea in which two entirely different systems of movement are briefly occupying the same space. A container vessel draws 40 feet of water below its keel. A humpback whale resting at depth is perhaps 60 feet below the surface. The margin is, at some points, and in some tidal conditions, not wide. The vessel does not know this. The whale may or may not have the time or the sensory information to respond. A whale traveling south through that channel at night, the lights of the shore faint on the water to the east, passes through the crossing point, and continues. Its tag records the position. Days later, the tag data arrives at a receiver on a research buoy, is relayed to a satellite, comes down to a ground station, and eventually appears as a dot on a map in a researcher's database, Slightly south of the channel, still moving, the track continuous and unbroken. The whale is south of the islands now, in deeper water, in open ocean, still heading for water it has never seen, and that every biological system it carries is directing it toward, with a certainty that requires no knowledge of destinations, and no map any human has drawn, only the slow, ancient, reliable signal of a planet tilting on its axis, and the body that has learned over long time to read it. The thermal front the whale will cross tomorrow is already visible in satellite data, a pale color boundary running southwest across the image, where two water masses press against each other in the long, slow grammar of ocean circulation. The whale does not know the front is there. When it arrives at the temperature change in the water, it will register the gradient and respond to it as its biology directs, and the response that proves most useful across the long history of this migration is to move along the cold side, southward, where the prey concentrates and the temperature guides the route. The two whales that left the same feeding ground on the same October morning, one coastal, one pelagic, will find the same front eventually at different points along its length, and both will follow it toward the same destination, each tracing its own path through an ocean wide enough to hold them both without either one knowing the other is there. They arrive within weeks of each other in warm, shallow water far south of any winter. The temperature here is more than 20 degrees warmer than the water they fed in at the beginning of autumn. The light is different, brighter, more direct, the sun reaching higher in the sky. The water is clear and shallow over coastal banks and reefs, and the sounds of other whales carry through it from a distance. The long southward line of the migration ends here, in this warmth, in this company, in the biological business of a breeding season that the whole months-long crossing was made in service of. The ocean. The two whales crossed to reach this place, its fronts and its upwellings, and its shipping lanes and its waiting predators, and its long stretches of empty blue, falls behind them the way any landscape falls behind a traveler who has passed through it and arrived. It is still there, exactly as it was. The cold, productive water of the feeding grounds is still filling with the short polar summer's growth. The shipping lane in the Santa Barbara Channel is still being crossed in both directions through the night. The transient killer whales are still holding station at the headland, waiting for the northward migration that will come when the season turns again. And two whales that left the same place on the same October morning rest, now in the same warm water at the end of the same long arc, having crossed entirely different oceans to get here, arriving at the same still, enclosed warm shallows, where the journey finally settles into rest. Somewhere over the open South Atlantic, far from any coast, a bird the weight of a folded letter banks into a wind it has been riding for hours. The sky above it is pale and enormous. The water below it is dark. Between those two surfaces, there is almost nothing. No tree, no rock, no shadow of a reef, only the long heave of ocean swells moving in slow procession from west to east, and the bird cutting across them on wings held nearly still. This is an Arctic tern, and the line it draws through the air is one of the longest any creature traces in a single year. From its breeding grounds above the Arctic Circle to the edge of the Antarctic pack ice and back again, the route curves and bends and doubles on itself in a great sinuous arc that follows the wind systems of two hemispheres rather than the straight geometry a map would suggest. Researchers fitting small geolocators to terns in Greenland and Iceland have tracked individuals covering between 44,000 and nearly 60,000 miles in a single annual cycle, not in a straight line, but in a looping, wind-shaped path that sweeps down through the eastern Atlantic, bends west along the Antarctic convergence, and climbs back north through the western Atlantic or across the Indian Ocean, depending on the year and the wind. The total distance varies. The underlying logic does not. The bird is reading the atmosphere the way a sailor reads the sea, finding the pressure gradients and the prevailing flows that will carry it forward with the least effort, converting planetary meteorology into free passage across the width of the world. The tern weighs roughly 3.5 ounces. Its wingspan is not quite as wide as this page is long. In the physics of flight, it is almost nothing, a hollow-boned envelope of muscle and feather and hollow air. Yet the total distance it covers in a lifetime of migration, accumulated over 20 or 30 years, may exceed 1.5 million miles. That figure needs no performance. It sits plainly in the arithmetic of the thing, as quiet and steady as the bird itself, riding a gradient of pressure over a sea no human will ever walk. The route the tern flies is not a straight pole-to-pole crossing. Straight lines across ocean would spend too much time fighting headwinds. Instead, the bird plots itself into the heart of the great atmospheric circulation cells that organize global wind patterns, the trade winds pushing equatorward in the tropics, the westerlies roaring across the mid-latitudes, the polar easterlies wrapping the ice caps. It enters these systems at angles that allow them to act as conveyors, tilting the bird along corridors of moving air rather than forcing it to stroke against an opposing mass. The detour is not waste, it is efficiency. A longer route, flown partly on borrowed wind, costs less energy than a shorter route fought into a headwind for 1,000 miles. Over millions of years of selection, the survivors were the birds that found the good air. The route that remains is the one those birds carved out, revised, and handed on. A bar-tailed godwit stands on an Alaskan mudflat in late summer and does not look like a creature preparing to cross the Pacific Ocean. It looks heavy. Its belly is distended with the fat it has been laying down for weeks, in a process that has nearly doubled its body weight since the breeding season ended. The flanks that were slim in July are thick now, swollen with stored lipid, and the bird moves with a careful deliberateness, feeding steadily at the margin of the tide, still adding mass day by day. Inside its body, something stranger is happening. The gut is shrinking, the liver is shrinking. The organs of digestion, the long-coiled infrastructure of absorption and processing that would be essential for any ordinary journey, are being quietly dismantled, their tissue converted into fuel. A bird preparing for a transoceanic flight is, in one precise biological sense, consuming itself in order to become ready. The machinery it will need on the other side can be rebuilt from scratch when it arrives. What it cannot carry is extra weight, so the gut goes first. When the godwit finally lifts from the mudflat and turns south over the open Pacific, the distance remaining before it touches land again is approximately 6,800 miles. It will cover that distance without stopping, without landing on water, without feeding, without drinking. The flight lasts between 8 and 11 days. Satellite trackers attached to Alaskan birds have followed their signals across the open ocean, past the Hawaiian Islands without pausing, past the equator without pausing, all the way to the tidal estuaries of New Zealand, where the signal finally stills on solid ground. The longest recorded non-stop flight of any bird, and among the longest non-stop movements of any air-breathing animal, belongs to this particular creature on this particular corridor, driven by a hormonal imperative and navigating by a time-compensated sun compass that accounts for the shifting azimuth of the sun as the bird crosses latitudes and time zones hour by hour. A humpback whale moving south through warm Pacific water is, in metabolic terms, doing something recognizably similar to the godwit crossing open ocean. It too is traveling on stored reserves. It too is not eating. The blubber that built up through months of polar summer feeding is burning away steadily with each day of transit, each hour of sustained swimming, each breath drawn at the surface and expelled in a low mist that drifts behind it on the wind, that drifts behind it on the wind. But where the godwit completes its crossing in days, the whale takes weeks, and where the godwit weighs less than a pound at departure, the whale weighs tens of thousands of pounds at peak summer condition. The strategies are the same in their broad architecture: store fuel, suppress non-essential systems, cross the distance, but the scale is oceanic in the one and barely measurable in the other. Both solutions work. Both have persisted across millions of years of selection. The ocean holds them both at once, one close to the surface and one far below, traveling in parallel through the same ancient seasonal imperative. Somewhere in the dark cold of the northeastern Pacific, moving through water that holds its temperature just above the point where a human hand would go numb within minutes, a leatherback sea turtle makes its way south. It is not fast. It is not built for speed. Something it is built for is warmth. Specifically, the retention of a core body temperature significantly higher than the water surrounding it, maintained not through any metabolic furnace, comparable to a mammal's, but through a combination of sheer mass circulatory architecture that prevents the flippers from bleeding heat into the sea, and a layer of oil-infused tissue that insulates in ways no purely scaly skin could manage. A leatherback is a cold-blooded animal that has evolved to behave thermally like a warm-blooded one, without any of the enzymatic or hormonal machinery that keeps a whale or a seal or a bird at constant temperature. It achieves the same result by different means. The ocean that would chill a smaller reptile to immobility in hours is merely cool to a leatherback moving steadily through it. The distances leatherbacks cover between their tropical nesting beaches and their high-latitude foraging grounds vary more than almost any other migratory animals. Satellite-tagged individuals have been tracked on one-way journeys of nearly 4,000 miles, and some Pacific leatherbacks appear to cross from nesting beaches in Indonesia to feeding areas off the coast of Oregon and British Columbia, a passage of more than 7,000 miles across the widest ocean on Earth. They are not following coastlines. They are crossing open water toward jellyfish blooms and soft-bodied prey, concentrated in cold, productive seas, driven by the same fundamental logic that pulls humpback whales toward Antarctic krill. The richest feeding is at high latitudes, and the safest place to lay eggs and hatch young is in the tropics. And between those two places lies a great span of ocean that must simply be crossed. The thermal problem the leatherback solves is one the whale solves too, but with entirely different anatomy, arrived at by entirely separate evolutionary paths. A baleen whale is descended from land-dwelling mammals that re-entered the sea roughly 50 million years ago. A leatherback's lineage has been marine for far longer. The turtle body plan is ancient in ways mammal bodies are not. What they share is not ancestry but outcome, a capacity to maintain useful function in water cold enough to strand or kill most other air-breathing animals of their size. The solution took different forms in different tissues: blubber in one case, gigantothermy and countercurrent circulation in the other. But what each produces is a body that can be present in cold water long enough and consistently enough to make the high-latitude journey worth completing. On the floor of a mountain forest in central Mexico, in a stand of oyamel firs at an elevation of nearly 10,000 feet, the bark of the trees is not visible. The trees themselves are not visible. Every surface, every branch, Every needle, every inch of trunk from root to crown is covered in orange and black wings folded together in sleep, so densely packed that the trees seem to have grown bark made of insects. 1 billion monarch butterflies have gathered in this forest from the eastern half of North America, and the weight of them bends the branches. The forest moves when they move, which in cool weather is barely at all. The cold slows them, holds them in the tight mass on the trees, where shared body heat helps all of them survive the night. When the sun reaches the canopy in the morning and the air begins to warm, the wings begin to open, slowly at first, one here and one there, and then in great orange sheets that lift from the trees and fill the light. Each of these butterflies flew between 1,500 and 3,000 miles to reach this forest. None of them has ever been here before. The individuals that make the southward autumn migration are a special long-lived generation, several months old, rather than the 2 or 3 weeks. A summer breeding monarch typically survives, and they navigate with a time-compensated sun compass housed not in a brain structure comparable to anything in a bird or a whale, but in the antennae themselves, where circadian clocks track the sun's daily arc and allow the butterfly to extract a southwesterly heading that holds even as the sun moves across the sky. They are using daylight as a clock and as a compass simultaneously, solving a geometric problem that would require careful calculation in a human navigator, in a nervous system smaller than a grain of rice. The northward return in spring is not made by those same individuals. One long-lived generation flies south. 3 or 4 short-lived generations complete the return north, each laying eggs along the way at the milkweed patches appropriate to their season, each living only long enough to advance the wave a few hundred miles before dying and leaving their larvae to become the next generation. No individual monarch knows the full route. The complete round trip exists only at the level of the population, distributed across time and generations in a way that has no parallel among whales, which may travel with the same individual mother over many seasons, the route passing from body to body through direct experience. In this sense, the butterfly carries a kind of knowledge that is the opposite of cultural transmission, where a humpback calf swims beside its mother across thousands of miles of open ocean and learns the route by following it. The monarch carries no learned route at all. The forest in Mexico, the heading, the timing, the response to the sun's geometry, all of this is encoded in the genome, refined over enormous time by the deaths of butterflies that flew the wrong way, arrived too late, or chose a forest that no longer stood. The map is not in the individual. The map is in the inheritance. Both solutions have persisted. The whale's cultural transmission and the butterfly's genetic encoding are equally functional, equally ancient in their respective lineages, and arrived at by completely different evolutionary paths for completely different reasons. One works because the mother is present and the journey is long enough to teach. The other works because the mother is absent and the destination is fixed enough to encode. The ocean accepts both. A California beach in January holds a very different kind of traveler. Northern elephant seals haul themselves from the surf at colonies along the central coast. Enormous animals, the bulls weighing up to 4,000 pounds, their blunt faces and inflatable proboscises making them look less like mammals than like something that should not exist on dry land, which is perhaps accurate. They spend only a fraction of their year on shore. The rest they spend at sea, in movements that cover distances comparable to a humpback whale's annual migration, but in a pattern so different in structure that the comparison reveals more about what migration means than either animal does alone. Adult male elephant seals travel to foraging areas near the Aleutian Islands in the North Pacific, following a great northwest arc that takes them into cold, productive waters along the edge of the continental shelf and the deep ocean beyond it. Adult females travel to an entirely different part of the same ocean, further south into subtropical open water regions where their preferred prey, midwater squid and fish, are concentrated at depth. The same breeding beach, the same species, the same general season, and yet the males and females spend their months at sea in regions hundreds of miles apart, the ocean sorting them not by individual preference, but by the demands of sex differentiated physiology. Males, larger and requiring more calories per dive, pursue larger prey in richer northern waters. Females, diving deep into the mesopelagic zone for smaller, more dispersed prey, range through a quieter and more southerly sea. The total annual distance an adult male elephant seal covers may exceed 13,000 miles. That figure includes two separate migrations per year, one after the breeding season in early spring, one after the molting season in summer, giving these animals a travel schedule more complex than a simple pole to tropics return. They are not following a single axis. They are making two separate long-distance excursions, each to a different part of the ocean, each lasting several months, with brief intervals on shore in between. If a humpback whale's year is organized around a single long axis between cold and warm, an elephant seal's year is organized around a sequence of departures and returns, the beach as the fixed point and the open ocean as the recurring destination. Both animals return to the same shore. The elephant seal hauls out on the same beach year after year, and the satellite tracks retrieved from tags recovered at those beaches show departure headings consistent across years, arrival zones that overlap in space, foraging regions that are consistent with individual experience. There is no one following anyone. Each adult seal carries the route inside it, learned over seasons of trial and revision in the open North Pacific, the individual biography of an animal that has solved the ocean by spending years inside it. A humpback whale at depth in warm Caribbean water is surrounded by sound, not the broadband noise of a busy shipping lane or the crack of breaking reef, but the lower, more resonant sounds of a breeding ground in full activity, long tonal sequences produced by males in the surrounding water, carrying over distances that render individual distance meaningless, the whole region sonically occupied in a way that has no analog in anything happening above the surface. The water is warm enough that a hand trailing from a boat would feel it as comfortable. The visibility through the blue is tens of feet in every direction, the water so clear that a whale 40 feet below the surface is visible from above as a gray shape suspended in light. This is one end of the migration. The other end, the feeding ground, the krill-dense polar sea, the cold productive water where the months of fasting are finally broken, is thousands of miles away. Between those 2 points, the annual path of this animal has been laid down over a lifetime of passages, each year's route slightly adjusted for the particular conditions of that season, but converging on the same waters, the same general region of the same warm sea, within days of the same point in the annual cycle. The calendar is internal, the destination is fixed. The route between them is a lived thing, accumulated season by season. An Arctic tern crosses that same ocean on its way south. It passes through the same latitude during its own migration. The equatorial waters the tern transits in a day or two, representing the same belt of ocean where the whale may spend weeks. From above, the tern is a white flicker against blue, visible for a moment, and then gone. From below, it does not exist at all. The ocean surface is a ceiling broken only by the whale's own exhalations, and the air above it belongs to a different world entirely, inhabited by creatures with hollow bones and beating wings that do not register in water. The tern does not know the whale is there. The whale does not know the tern is passing. And yet both of them are solving the same problem, the geographic separation of the best place to feed from the best place to breed, with bodies so different that they might as well belong to entirely separate universes. One of them weighs a few sheets of paper. The other weighs as much as a loaded truck. One crosses the distance in days. The other takes weeks. One navigates by the geometry of the atmosphere. The other reads the magnetic field and the remembered shape of ocean floor. The ocean does not know they are using it differently. The ocean is simply there, enormous and various, carrying both. A bar-tailed godwit, descending through evening light toward a New Zealand estuary, has been in the air for 9 days without landing. Its body is a fraction of what it was when it left Alaska, the fat stores nearly gone, the flight muscles used down to their limit, the digestive organs that were shrunk before departure, not yet rebuilt. It drops toward the water with a visible heaviness, a deliberateness in the descent that is different from the easy wheeling of a bird with reserves to spare. It lands in shallow water at the edge of the mudflat. It does not move for a long moment. Then it begins to feed. Somewhere in the Pacific, a humpback whale that has completed its equatorial winter will have begun its northward return already. The hormonal signal of lengthening days, reaching through the warm water, even at these latitudes, the body beginning to reorient toward the cold and the krill. The godwit and the whale are both in motion, or both recently arrived at the same point in the planetary year. The planet's tilt is the clock they both obey, not a decision, not a calculation, but a response encoded in bodies, shaped by selection to be sensitive to the one thing the Earth does absolutely reliably, which is to change the length of its days. In the mountain forest in Mexico, the monarchs will have begun to stir as the days lengthen past the winter solstice. In the Southern Ocean, Antarctic krill will be deepening in the water column as summer light penetrates the sea. On a California beach, elephant seal pups born in January will be growing toward the weaning day when their mothers leave them and return to sea. Everything is moving, or about to move, or recently arrived from moving, the whole system of migrations turning in its annual cycle like something very old and very slow, all of it organized around the one reliable fact of a planet that tilts and turns and brings its seasons back without fail. A leatherback moving through 50-degree water in the North Pacific is perhaps 3,000 miles from the nearest nesting beach where it came ashore 2 years ago and will come ashore again in 2 years more. Its body temperature is held above the surrounding water by mass alone, dozens of degrees warmer inside than out. The heat generated by muscular effort and the slow burn of digested jellyfish. But Pine Blue's held within the body by the architecture of a circulatory system that short-circuits heat loss before the flippers can bleed it into the sea. The turtle does not know it is warm. It does not experience its own thermoregulation as anything other than the ordinary condition of being alive. The cold sea is simply the sea. The jellyfish bloom somewhere to the northeast is the direction of food. The whole planetary thermal problem is solved without awareness, in tissues that have been solving it for longer than the genus Homo has existed. In this, the leatherback and the humpback are alike, and the godwit and the tern and the monarch and the elephant seal are alike, and all of them together are alike in this one thing. None of them is trying. None of them chose the route. None of them solved the problem. None of them feels the achievement of having crossed an ocean or a continent or half the atmosphere of a planet. What moves them is older than intention and quieter than thought. It arrived in their bodies the way all functional structures arrive, carried forward by the ones that worked, tried again in each generation, refined over spans of time so long that the word refinement barely covers the scale of revision involved. What remains is what worked. What works is what moves. The turn that banks into a South Atlantic tailwind does not experience the tailwind as a gift or the root as a discovery. It enters the moving air because its body is built to enter the moving air. The godwit that shrank its own gut before crossing the Pacific did not calculate the metabolic trade-off. The calculation happened in the cells, in the hormonal cascade that autumn photoperiod triggers, in the cellular signals that instructed the digestive organs to give their mass over to the flight muscles. The monarch that holds to a southwesterly heading across a sky it has never seen before does not consult the compass in its antennae. The compass runs continuously, automatically, calibrated by a clock it did not choose to carry. The whale mother descending into warm Caribbean water with her calf close at her flank is transmitting something that the godwit's chick and the monarch's next generation will never receive. A direct experience of the route, traveled in company, learned through proximity. The calf knows the journey because it took the journey. When it makes the crossing alone for the first time the following year, it will carry a route made partly of inherited biological predisposition and partly of actual memory, the warmth of a particular current, the depth of a particular trench, the quality of light at a certain latitude in a certain season. How large each contribution is, no one yet knows precisely. The truth is likely somewhere in the middle, in a blend of genetic endowment and lived experience that no clean experiment has yet separated. That uncertainty is not a problem. It is simply the condition at the edge of what measurement can reach. The whales keep migrating regardless. An Arctic tern gains altitude over the South Atlantic, and the horizon curves away below it in every direction. The water is so far down that individual waves are invisible. Only the larger patterns of swell are discernible from this height, and those patterns tell a navigator which way the deep ocean is running. The tern holds its course. The wind carries it.